Okay, good morning, everyone. Welcome to next session of this amazing meeting. So we're going to have two talks. The first by Camilo. So please go ahead. And then there will be, of course, the discussion session. So please keep questions in mind also for Camilo, because in the last couple of days we see that people tend to ask to the last speaker. Yeah, and this shouldn't be the case now. So please, keep them in mind. So please, Camilo.
Thank you, Diego. Good morning, everyone. First of all, let me thank the organizers for the invitation. I'm going to talk about two papers, essentially, that were done in collaboration with Valerie, with Song-Mook Lee, who is in the audience, and Nick. So here is the outline of my talk. I decided to just show or focus on the new aspects that I think were important this year on this thing. So on the development of, on the detection of gravitational waves in haloscopes. But before discussing those, I will just explain how this works and what's the main idea behind this. And for doing this, we have to go back to the ideas of Gerstenstein. He was the first one who proposed this method to detect gravitational waves by means of external electromagnetic fields. And I find this very interesting because he was also one of the proponents of the use of terrestrial interferometers to detect gravitational waves, actually 1 year after, or 1 year after proposing this idea of the that's called today the Gerstenstein effect. And what is the Gerstenstein effect? Well, actually, the inverse Gerstenstein effect, to be more precise here. So the idea here is that once an electromagnetic wave enters in a magnetic field and uniform magnetic field, according to Einstein, this gravitational wave is a perturbation of space and time. So it will create oscillations within this magnetic field. It will perturb the magnetic field, will make it oscillate. According to Maxwell, this perturbation in the magnetic field will create another electric field, and this will continue generating a photon or an electromagnetic wave. And then that's the essential principle behind this. Okay. Now a few things about the inverse Gerstenstein effect. This is not quantum gravity. This is just a classical process. It happens in GR plus electromagnetism. The rate of conversion does not involve the Planck constant, so it's a purely classical process. It can happen on cosmological scales. I studied that with Valerie, and actually that's how we start thinking about this thing. And what is more important, I guess, related to my talk, is the fact that this conversion is strictly analogous to axion dark matter conversion. So axions do the same thing. And that's why people have tried to recast limits on axion searches, limits on axions from different experimental searches on gravitational waves. Okay, so here is an example. This is by this famous paper from Aldo that was mentioned many times during the workshop. And here, what they do is essentially, okay, so in let's say in Alps, they try to study this conversion of axions. So first you produce the axion in the lab, then there's this wall in the magnetic field. Once the axion is produced, then it will be again converted back into an electromagnetic wave. But if you don't have this part on the left, you can just simply focus on the right, and then if you have a gravitational wave entering, the gravitational wave will interact with the external magnetic field, creating an electromagnetic wave. And then there's a detector, and you could place a bound on gravitational waves if there is no photon found in this. Okay, so I actually in this paper they presented these limits and compared this against a few benchmarks. And currently with Andreas, we are working on calculating the complete spectrum of gravitational waves from the sun. And that's, so I adapted this figure from this paper. I adapted this figure, but I put the actual spectrum. I'm sorry. So this is the spectrum of the sun. Just to say, so I'm mentioning this because it was mentioned on Monday, and I think it's important to emphasize that this is a purely standard model process. This is not physics beyond the standard model. It doesn't have pre-parameters. It can be calculable. I mean, it's calculable. I mean, it's difficult, but it's calculable. It extends over many decades in frequency. And actually, it's essentially a calculation that was started by Weinberg. And yeah, now we are trying to put all the pieces together. And as you see, I think it's important to emphasize this is a standard model. And so when people say, okay, if you detect high-frequency gravitational waves, that's smoking gun of physics beyond the standard model. That's, I mean, in the light of this, that's probably not true. And it's also important to, sorry, I keep going back and forth. It's also important to emphasize that even though these things are not subject to the BBM bound, because they are produced in the sun, not in the early universe, there is still, so in terms of sensitivity, they are below the sensitivity that you need in order to probe signals that can escape the BBM bound. Okay.
What sets the scale of the peak in the solar gravitational wave spectrum?
So there are two scales, actually. You can see them here. I would just say that, okay, this is very similar to the to the calculation of the gravitational waves from the from the Big Bang, so from the thermal plasma in the early universe. You have first a contribution coming from hydrodynamic fluctuations, and that's this part here. This is essentially hydrodynamics. Then in this part, you have the contribution by Weinberg, which is the dominant contribution, and it's actually, he calculated the total power, and the total power is currently described by this part of the spectrum, that's Bremsstrahlung. And then at the end, so Bremsstrahlung of so collisions of protons and electrons in the sun, Bremsstrahlung gravitational waves. And this part of here at the end of the spectrum, you have a small contribution from photoproduction, which is similar to what people in the Axion community call Primakov effect, but for gravitational waves.
But you said the left-hand part of the spectrum is dominated by hydrodynamic fluctuations. Then what sets the cutoff for that? Because it seems to be rising as a power law, but then something has to set the cutoff.
Yes. So what sets the boundary between these and this is the collision frequency of the particles in the sun. So essentially, this determines when you have a transition from macroscopic description, which is the Bremsstrahlung, to something macroscopic, which is the hydrodynamic fluctuations. Okay, but the talk is not about this.
Can I ask
yes.
a question?
Yes, okay, good. So I wanted to mention this, and I think it's important to emphasize.
Can I ask another question regarding this? Can you do the same calculation for our planet, for example? I think they're...
Yeah, this is actually... you could, but the thing is that, okay, first of all, the temperature of the planet is much lower, and second of all...
I know.
the number of... I mean, this is like that just because the sun is very massive, so it has many particles inside them.
But it's possible in case you have already the model.
Yeah, you can. Yeah, it's possible, but this is going to be dominated by the sun.
Inside the Earth, there's something very hot, so we can take a limit.
But I think this is going to dominate by far. Yeah.
Okay, thank you.
Good. Okay, but let's go back to haloscopes. So how does it work? So I told you about the Gerstenstein effect, but that's just an example of Axion electrodynamic, so gravitational wave electrodynamics. And as I told you, a lot of people have studied Axion electrodynamics in different contexts. So there are more things beyond just this simple conversion of gravitons into photons. So what is the general principle behind this? So the general principle you can think of in terms of effective currents. So this is very well known for the people who do axion physics. So when an axion enters a region where there is an electromagnetic field, these two together will create an effective current. So they will source the mass pulse equations and create effects. Okay. These are not real currents. This is important to emphasize. Actually, given the discussion we had yesterday, I think it is important to say again and again, these are not currents of electrons. These are not currents of anything. This is just a mathematical artifact that is useful to describe the physics in this experiment. And the thing is, gravitational waves do exactly the same thing. So if you can write down in a fully covariant way Maxwell's equations in curved spacetime, but you can, if you assume a few things, so like, well, of course, that the wave is, the amplitude of the wave is very small, and well, one has to think of what happens with the external currents, etc. But that was the discussion from yesterday. But I mean, the bottom line is you get an effective current, and the effective current looks like this. So in a way, an experiment that is designed to detect effective currents for axions can also be used to detect gravitational waves, just because gravitational waves do the same thing. Good.
So if you write things in that way, then the left-hand side of the inhomogeneous Maxwell equation looks as usual in flat space, and all the corrections are absorbed into that current, right?
Say that's an effective description, exactly. So you just don't have to deal with the full covariant thing if you just use this effective approach. Yeah.
Thanks.
And what is the meaning of this effective current then?
So this effective current is simply encoding the effects of the gravitational wave. So you can just forget about the rest, the gravitational wave. Well, there are two things. Well, maybe I will discuss this more at the end. There is an additional effect, and it's the fact that, so on top of this, so on top of the effective current, you also have, in the detector frame, the fact that the gravitational waves induce a Newtonian force. So you have these two things. So you have, so let's say the gravitational wave in this, so in this particular setup, in this context, this is very important. I'm not talking about the full general thing, because sometimes, I mean, yesterday in the discussion, it was clear that, I mean, people try to perhaps extend this to more general context, and that's probably not true. So in the case of a specific experiment on Earth, or well, when you try to determine the effect of the gravitational wave, there is an external magnetic field produced by cables and things like that.
But can I say something? You said you said it's just a mathematical. You didn't give any physical meaning, and I think the question is, I was asking the physical meaning. I would say it's a transducer, which transduces one energy into another, and we have that in normal when we convert mechanical energy into electrical energy. It's a similar thing. You modify Maxwell's equations.
Yeah, so it creates... So
there is a physical significance to it.
There's a physical significance. It's sourced.
You can't just say it's a mathematical thing that, you know...
It's a mathematical thing in the sense that, okay, what I want to say is that this is not...
You're creating electricity. It's a transducer.
Exactly. So the electromagnetic, the gravitational wave is creating an effect, but I'm just saying this is not a current of electrons. That's the point. It's not a current of protons.
I'd call it a transductance between gravity waves.
Okay, but let's just...
Let me, since there will be the time dedicated to discussion that is not in the talk, because otherwise you're not going to get to the point.
Yeah, of course.
I suggest that these kind of questions are asked in the discussion session. So,
and there was also a discussion yesterday on that.
So we'll let Camilo at least get to have his talk or something.
Yeah, so let's just go to haloscopes based on loop element detectors. So that's, I have in mind with this something like abracadabra shaft. So here what they do, so forget about gravitational waves for a second. So what they do is they're searching for axions. And the way they do this is, again, by searching for by these effective currents induced by the axions. So you have dark matter, which is everywhere in the galaxy, right? It's sitting there. It's dark matter of the universe. It's in the halo of the universe. That's why this is called a haloscope. Then you have a very strong magnetic field in this volume. Then, due to this effective current, you source a magnetic field in this case. And the magnetic field, so if there was no current here, no effective current here, in principle, you don't expect any magnetic flux here at the center. But if you do have this current, which again is not a current of electrons, you will source a magnetic flux. So if you put something there to measure this, you will detect axions. Okay, so that's what they are. In a sense, this is what they are doing. Of course, this is more complicated, but I mean the bottom line is this, right? And then, as I said before, I'm a disaster with this. Sorry. One can use the same for gravitational waves, okay, using this effective current, okay? So the gravitational waves enter in this region where there is a magnetic field. You source a magnetic flux at the center due to the appearance of this effective current. And here you have, in this plot, you have the magnetic flux, sorry, not the magnetic flux, the magnetic field that appears as a result of this effective current. So yeah, these are the contours of the component along the z direction. Good. So actually, when we did this for the first time, we were very surprised by many things. It's very interesting. So one thing is, okay, gravitational waves, as you all know, your gravitational wave experts, are described or have two polarizations. And somehow in these sort of detectors, there is only one polarization that couples. Somehow the H plus does not give a signal. And also, what you find is that there is a suppression at small frequencies. So the gravitational wave induces a flux that goes with the frequency cube. And in these sort of experiments, the frequency times the relevant distance is, I mean, this together is very small. So this gives a suppression. And that differs with respect to axions. So
is this coupling only to the cross-polarized gravitational wave independent of the direction in which the gravitational wave arrives?
Yes, in this particular case, yes. Actually, you see here, this angle here is the direction.
Mm-hmm.
Yeah. So okay, so actually, what we tried to do this year and well last year, or after we finished this paper, was to understand this in a broader context. And
sorry, why is linear in B and in H? Usually the flux should be quadratic, isn't it?
No, in this so in cavities, I think you might say that, but here it's not because so the effective current is linear on the gravitational wave, and the magnetic flux is linear on the current. So the whole thing is so the magnetic flux is linear on the gravitational wave. So it's different. It's a different a different dependence. Okay, so what we did in that paper, so in the first paper, what we did was like, okay, this is very, after thinking about it for a long time, we realized that this is just a consequence of the fact that the experimental setup is highly symmetric. So you not only have a toroidal symmetry, so you have cylindrical symmetry, toroidal symmetry, you have the pickup loop itself is circular, so you have a lot of symmetries, and you know gravitational waves don't couple to very symmetric systems. And this is an example of that. So what we did was, okay, just break it. Just break the symmetry somehow, and there was this idea of using a figure 8 pickup loop. So instead of having a loop that is circular, we proposed this idea of having a figure 8 instead. And what you see is that here is the sensitivity of these experiments to gravitational waves, and then you see this is the what you would find, the improvement that you find if you change the pickup loops, and you see this quite substantial. And yeah, and I think this is very interesting because, okay, from my point of view, so theorists playing with this can, so the experiments were not designed to detect gravitational waves, but nevertheless we managed to put limits on gravitational waves. I mean, they are small, yes, but I think at this frequency range, this was actually important. And also we managed to propose ideas to make it significantly better, and this is what you see in this plot. Okay, there will be a dedicated.
So why do you get a limit at all with the circular pickup loop? Because as you said, gravitational waves don't like to couple to circular things.
You get a limit for one polarization. You don't get a limit for the H cross, you get a limit. For the H plus, you generate no flux. So
and the limits in the plot that you showed, was this on cross-polarized?
Yes. So yeah.
Okay.
Or on a wave that is unpolarized, and then you just put a limit. You can only place a limit on the H cross.
So the flux, of course, remains the same. It's just the response of your detector.
Yes.
That's different. Mm. Okay.
Good. So there will be a dedicated talk on abracadabra by Kylore next to me, right next to me. So okay. So what we did, so that was the first paper. In that paper, we just really focused on these toroidal symmetries, and we did not provide a deep explanation for these cancellations. But we continue this work this year when Sam Lee joined us in these efforts, and he was very good in calculating things, and this is very important for this stuff because it's very hard to calculate. Well, not very hard, but very, yeah. It's a lot of tedious calculations. So we extend our calculations to solenoidal configurations. And yeah, so putting everything together, this is what we find looking into the future. So these are different experiments with different symmetries, not only toroidal, but also solenoidal. And yeah, so you have dark matter radio with the A pickup loop. You have this 50-liter thing, the GUT, the meter cube. You have this WISP LC. And okay, so I have 5 minutes. I don't really have a lot of time. So I know there will be a dedicated discussion tomorrow on how to compare signals. In our paper, we propose an idea of how this should be done. And essentially, the idea is to introduce a coherence ratio in order to recast Axion searches, taking into account the different time scales that are involved. And yeah, so, but I guess well, for now I will not discuss this. But okay, these plots assume a coherence ratio of 1. Okay, so in reality, this might not be the case because of what I said. I mean, of course, if you have an axion that is a persistent signal, and if you have a transient gravitational wave, there are time scales that will not allow you to simply compare directly fluxes like that. But we just assume this and discuss other benchmarks with other coherent ratios in our plot, in our paper. And also, I know there are other methods, and okay, this could be discussed tomorrow. So let me tell you a little bit about, so in a way, your question. So what happens if you, so we start noticing that actually the fact that one polarization decouples, depending on how you measure, is actually very generic. So as long as you have cylindrical symmetry, and yeah, so you typically have always that one polarization decouples. So this is an example. It's a bit. I mean, this is just an illustration to tell you. So if you put you might have two. I mean, typically you have two external fields, solenoidal or toroidal, and you can place the pickup loop. So the thing that measures the magnetic flux in different orientations, and in those cases you find different fluxes, and in those cases, for instance, let's take this one. So here you only have a signal with the H plus polarization. Here you only have a signal with the H cross, and so on. No? And on top of that, sometimes you have a suppression with the frequency square. Sometimes you have a suppression with the frequency cube. All this indicates that there are selection rules. I mean, you have an experimental apparatus, and there are selection rules, like in quantum mechanics, right? So, well, the first thing to say is that the omega square dependence is unavoidable because, okay, unavoidable because and you can see this in the proper detector frame. assuming that the frame, so that the apparatus is rigid. So in that case, the gravitational wave is always proportional to omega square, and all the effects are, of course, proportional to this. So that means that the flux must be necessarily proportional to omega square. So this suppression with the frequency is unavoidable. But in addition, so we found, we wrote 3 selection rules. The way I think of this is, okay, you write a detector response matrix for a wave coming from an arbitrary direction, impose cylindrical symmetry, that's important. So you impose cylindrical symmetry on this detector response matrix, and then you find with a little bit of work that this holds true. So first, that for an instrument with azimuthal symmetry, the flux is proportional to only H plus, so the H cross decouples. You have this suppression with omega square. So for an instrument with azimuthal symmetry, the flux is proportional to either H plus or H cross, but not both. And this holds to all orders in omega L under the assumptions that that is magnetostatic. And and for an instrument with full cylindrical symmetry, you only have even or odd powers of omega. Okay, so we put all this together. I think this was very nice because we managed to prove from first principles, let's say, how these detectors with high symmetry respond to gravitational waves. So we also found novel effects, and I think I have 1 minute, so I will be very fast. This is a bit of a I think this was extremely useful for us, but it's not necessary to understand the first part. But for us, as I said, calculations are usually involved. But what we found in this in the first paper is that one can simplify significantly calculations if one write the effective current as in terms of this P and M. This is essentially what you do in electromagnetism. These P and M's are effective, again, because this is not so these are not polarizations of material or anything like this. Again, as I was saying, this is an effective current, and therefore these P's and M's are just effective descriptions. People have done this. People in the audience have actually done this for axions. So for axions, you have this effective polarization or magnetization, and for gravitational waves, we notice that this can also be done, and this takes this form, which is extremely useful. And okay, one thing is that also gives insight on the problem, because we know that this, from just ordinary electrodynamics, we know that these things behave in certain way in order to make Maxwell's equation consistent. And one of the things that is important to keep in mind, I have 1 minute, I have 1 or 2 slides. So one thing that is important to keep in mind is that this thing, the Maxwell's equation, so you just take Maxwell's equations and work out the boundary conditions between a medium where there is a non-zero magnetic field and zero magnetic field. And you find, and this is one learns this in electrodynamics in first semester, second semester, I don't know, I forgot. One learns that whenever there is a discontinuity in this effective currents, or in this effective magnetization, you get a surface current, not a current on the bulk of this toroidal field, but an actual current on the surface. And it's very interesting because this is not found for axions. For axions, if you work out this structure, you find that simply vanishes, but that's not the case of gravitational waves. And somehow it's a sizable effect. It's not negligible. It has to be accounted for in these calculations. And also, this should be relevant for cavities. There was a paper today by Diego. Maybe we can discuss about this later, mentioning this topic tangentially. Okay, then there is, on top of this, the excitation of the mechanical modes, but I will not discuss this because it was discussed yesterday a bit and also by Sebastian on Monday. But essentially, the point here is that so everything we did was ignoring the fact that the experimental setup also reacts to the gravitational wave due to a Newtonian force that they induce. So we just neglect this. We assume that the experimental apparatus is completely rigid, that it doesn't change because of the gravitational wave. And that's not necessarily true. And in particular, it's not true if the at frequencies above the first mechanical resonance. And apparently, this can enhance the sensitivity. This was found by people in the audience this year. And these are my conclusions. I will just leave them there because I have no time. Thanks a lot.
Thank you very much. Well, there will be more time for discussion after the second talk. But while the speaker comes to the front, we can have some questions. Yes?
Yes, thank you, Camilo. For the estimations of the sensitivities you showed, you assume signals that remain coherent for how long?
So yeah, okay. So so we assume different things, but as I said, for these limits that we derive, we assume this coherent ratio to be 1, which means something very specific about I mean, it's an assumption, and this is probably not. It's not realistic if you think of gravitational waves produced by, for instance, mergers of black holes. But we just assume this RC equal 1.
Yeah, and in terms of really durations in seconds or things like that, you would be able to say to which duration it corresponds?
So if you change this assumption, then you will have to rescale the coherent ratio accordingly. So you have to calculate what would be the suppression due to a different time scale in the problem. And this will substantially reduce the sensitivity.
Okay, thanks.
Yeah, okay. I think we're going to stop here, but there will be more questions in the discussion session. So we can thank Camilo again and